And good evening, AP Physics students. Mr. Curson coming at you here. We're going to talk about potential tonight. I know my physics students have a lot of potential, but we're going to talk about electric potential. Specifically, Chapter 17, Problem number 9. And let's just go ahead and get down to it. Okay, in this problem, it states that I have two conducting plates, probably made out of some type of metal. And they're some distance d apart, and these plates are hooked up to a 200 volt power supply. When you hear power supply, I like to think about a battery. So I tried to draw a picture of a battery, kind of like the battery in your car, except maybe your car battery is like 12 volts. This guy is 200 volts. And I hook up these conducting metal plates to the battery. And what that does is it gives the top plate here a potential of 200 volts and the bottom plate here a potential of 0 volts. So there's a 200 volt difference between the top plate and the bottom plate here. Okay? And the question states, hey, what's the smallest distance I can put these plates and not have the air between the plates become conducting? Mr. Curson, what in the world does that mean? Well, here's the deal. Imagine I just keep increasing the voltage here. Eventually, there will be such a strong electric field in between these two plates that the electrons in air atoms will actually be torn off of their atoms and start to go this way, and actually the electrons would go this way, and you'd get a little lightning strike, you'd get a little spark. That's called a breakdown, right? And I know what you're thinking, Mr. Gerson, I'm about to have a breakdown right now. This electric potential stuff is hard. It is difficult. So anyway, what's the smallest distance we can have here without there being a big spark jumping across here? We don't like lightning. It's cool to see in the wilderness and outside, but in electronic devices, it's bad. Okay, so our new equation that we're going to use to solve this is this guy here. And it's an important equation. It's the connection between the electric field and voltage, between the electric field and potential, I should say, or potential difference. And what it says is, if I have a region of space that's, say, 200 volts and a region of space that's 0 volts, there must be an electric field between these. Specifically, you guys would be saying, yeah, Mr. Curson, there's an electric field in here, and it would point this way. And I know that because if I was a little small positive test charge, I would want to get repelled from these positive charges up here and attracted to these positive charges down here. Attracted to these negative charges down here. So there must be a connection between electric field and voltage. And there is. And it goes like this. You can kind of think of the rate at which the voltage changes with distance is equal to the strength of the electric field. And we use this equation so often that a lot of times physicists start to measure electric fields in volts per meter rather than in newtons per coulomb. And we'll take a second here in a minute and actually show that those two ideas are equivalent, a volt per meter and a newton per coulomb. Same units, but ends up being the same units or equivalent units. Okay, well, let's get to work solving this problem here. How close can the plates be before we have a breakdown of the air and a little lightning bolt? We're told that the air will start to conduct electricity when the electric field inside here gets to 3 million volts per meter. The voltage difference, the potential difference between the two plates is 200 volts. So let's go ahead and rearrange this equation, which should be D is equal to change in V over E, or 200 divided by 3 times 10 to the 6th And if we work that out here, we would get a d of, it's 6.6 times 10 to the minus fifth meters. But if we do our significant figures here, it ends up rounding to be 7 times 10 to the minus fifth meters. So that would be the smallest distance I could have between the plates without sparks coming across there. Mr. Kirsten, what happened to this negative sign here? Or why is this negative sign here? We should talk about that. Notice that the electric field points in a direction of decreasing voltage. So as I go from here to here, the voltage decreases, but that's the direction the electric field points. So the electric field points in a direction of decreasing voltage. That's why the negative sign is there. Okay, and for the distance here, really this is kind of a double negative because we know the voltage is decreasing here, and it's a negative and negative. So that's why we get that there. So that's will solve our problem here. I got a couple minutes left here, so I just want to highlight a couple ideas that we've been talking about. So this plate here is a conductor, right? Like a metal plate. And remember that the electric field inside a conductor will always be zero. Electrons are free to move around inside a conductor, and if there were an electric field inside one, the electrons would quickly rearrange themselves to cancel out that field. In other words, if there was an electric field inside this conductor here, and that electric field pushed the electrons this way, the electrons would all move that way until they created their own electric field, which canceled out the external field. So that's a good idea to keep in mind. Also, because of this, if the electric field inside a conductor is zero, then the voltage difference between any 2 points inside the same conductor must be zero. In other words, all points on a conductor will have the same potential. In other words, if this point on this conductor is 200 volts, then this is 200 volts, then this is 200 volts. Likewise, if this is 0 volts, or ground potential as 0 volts is sometimes called, 0 volts, 0 volts, 0 volts. And before we get to our joke here, just a little hint here on problem number 11. So keep in mind that voltage or potential is a scalar, all right? And a lot of times physics students like scalars because scalars have no direction associated with them. So problem 14, you can use this equation. If I have a charge Q and I want to know the voltage or the potential some distance r away from that charge, I can just use this equation, KQ over R, to find the potential here, right at that point. Notice it's R, not R squared. And if I have more than one charge, let's say I have plus 2Q here, and I want to know the potential here, I would just add up all of the point charges, and since potential is a scalar, I just add up all those values. Now they can be positive or negative, but there's no direction associated with potential, so I can just add them up. So use that as a hint on problem 14. By the way, as promised, I was going to show that a Newton per Coulomb is equal to a volt per meter. Well, what is a volt? It is a joule per Coulomb. And what is a joule? A joule is a Newton meter. So a Newton meter per Coulomb per meter is the same as a Newton per Coulomb. All right. Okay, I got 30 seconds for the joke here, and the joke is kind of a joke and kind of a suggestion. So I just started reading this book, and it's such a great book. It's called How Hippies Saved Physics. And it's the joke because it shows a naked hippie with an atom covering his bum, which is kind of funny. But it's called Science, Counterculture, and the Quantum Revival. And it talks about how quantum mechanics was really invented by some, out there ideas that went against mainstream science, and really invented by a bunch of young physicists. So fear not if you're feeling like physics is really, really hard. Fear not. It's the young physicists usually with really new ideas that really always take science to the next level. So that's both a little encouragement and a little humor and a reading suggestion. So David Kaiser, How the Hippies Saved Physics. Nice word, physicists. We'll see you tomorrow.